So after we had the clear idea of what is resistivity, what are resistors, now we will be looking at the arrangement of resistors. Now there are namely two types of arrangements that you can have. One is series, the other is parallel. Now what you have to keep in mind is, say suppose you have an arrangement of this kind. So this is point A. Now when I draw this, I assume that there is no resistance in this part. I assume this to be idle wire where it does not have any resistance. So after that, I apply a resistance R. Again I draw this. Say this is my RA. Then after some time, I again have a resistance. Say this is RB. And again my wire gets extended and this is my B. So now if we look over here, we have two points. These are 2 points and it has a potential difference. It has a potential difference. See the potential difference be VAB. This is the potential difference. Now what is interesting to observe is that, say suppose there is a potential difference. So we know that the charges, that is positive charge flows from higher potential to lower potential and negative charge flows from lower potential to higher potential. So for now let's assume, even though we had discussed if electrons are flowing in this direction, we can assume that positive charge is actually flowing in the opposite direction of the flow of electrons, or this is how electricity travels. So for now we have established in our previous videos this particular relation. So now coming back, what we can see is that it has two potential points. This is the ultimate potential points at the extremes, and because of these two potential points, charges starts flowing. Say suppose charge plus Q starts flowing. So now if charges are flowing over here, we see that this RA, what was resistance? Resistance was something which opposes the flow of charges. That is what we know as resistance. So because of this, flow of charges gets hindered. And so we can see that because of this resistance and because of this resistance, we see that the flow of charge in unit time is hindered. Okay, fine. Now I want to focus or highlight to a particular concept. Now look over here. If this much amount of charge is coming out of here, then the same amount of charge must also be received at the point B. It won't be happening that this charge after coming out of plus Q will stop somewhere at this point. This is stop. And this is completely wrong. This concept is completely wrong. Because if a charge is coming up, it will definitely come to this point B. Now what will happen is, because of this resistance, the flow of charge with unit time will be hindered. That is the work of resistance. Now therefore we can see that at a particular point of time, we can see that this is I. Flow of charge in unit time. Say suppose this much amount of charge is flowing in this much interval of time t. So this can be regarded as my current. So it does not matter whether this is the resistance, whether this resistance is spread out all over the place, or as soon as that one charge goes over here, it is being hindered. So because this charge is being hindered, the other charge which is of the same quantity as this charge won't be able to flow properly. Why? Because this is getting hindered, and this in turn will repulse the other charge. This is one of the way in which you can understand. So this charge opposes this, and this is opposed by this. Similarly, if it goes over here, the same thing happened. Because of this, the charge gets opposed. Charge gets opposed, and therefore, because of this too, the flow of charge suddenly goes down. Initially, before starting at this point, before going from this wire, it will see that it is not being able to travel. It is not being able to travel. So now we know, because it is not being able to travel, so the quantity of flow of charge from this point to this point gets hindered, and we can see that the current I decreases depending upon R. Now, the concept what I often see that students get confused is that the current as a whole, whether in this point, whether in this point, or whether in this point, will remain the same. Now I'm drawing this because it has been a bit crowded. So this is my B and this is my A. Now the flow is being obstructed because of this whole arrangement. So while coming out, this Q will be hindered itself. So what we can say is current as a whole will be same for all the places. That we know. So this is a concept that we have to know. Now, what we can see is current is equal in all the places. So they are known as series connection. And also what we have to see is that, say, this is the same current, but the resistance is different. So in order for say suppose an electron or for a charged particle to travel from this point to this point, it should experience a greater potential difference. That is, a potential should develop over here, and similarly if a high potential is developed over here, so this becomes a point of low potential. So because there is a development of high potential, it will push the electron for this higher resistance. So that's why this electron or this charge travel. Say suppose we are now talking about a charge plus Q. So this is the main concept. That is why you will see that sometimes while you keep reading books, you will see that they write this as potential, different potential but same current. Now what is this potential? Why is this potential not there for here? Now this is the overall potential. That is pushing the electron. Now there are individual potentials that has been developed just in front of the resistance. Because of this high and low potential, electrons are able to getting pumped from this point to this point, irrespective of their high resistance. And if you look over here, a potential is also developed over here because this is a resistance. It is resisting the flow of electrons. So what is pushing? If you ask me the question, what is the driving force for this charge to travel from this point to this point? Because there is a resistance. If there is a resistance, no neutral charge will flow because it is obstructing. So what pushes this electron from this side to this side? That is, there should be a difference in potential. This is difference in potential. So this is what pushes the electron. So if you look over here, VAB, that is V total, is actually equal to potential at point, I have named this as RA. So potential at A, this is A, or say suppose let this be 1. Let's name this resistance point to be 1 and this to be 2. So potential at 1 plus potential at 2. See, this is the potential that is getting developed and this is the potential that is getting developed. So now what you can see is the total potential, is because of these 2 points. The potential difference between here and potential difference between here. Because we have considered the rest, all the wires are resistanceless. So this is the concept that we can understand or have. So now we know that because this is connected in a straight line and the current does not change, so this can be termed as connection in series. So this is what we come to know. This is a series connection. Now what happens is, suppose this is my point A and we draw a wire and suddenly I separate these two wires. This is my resistance 1, that is RA, and this is my resistance 2, that is say RB. And then I join, This is my P. Now I know whatever the current that is flowing over here, this is the current that is flowing over here, is definitely coming back. So this is, we know by the law of conservation, you can understand this by the law of conservation of charges. Say whatever charge is going out of here, it must definitely come back to this point. Now this is connected. Say suppose this is connected. So whatever is going here, it should always be coming back. So no charge is there in the wire, in this particular wire. So now there is an interesting thing to know. Now if try to imagine this in terms of charge. Say suppose these are charges that is flowing over here. Now what you will see is that, say suppose this is a resistance and this is another resistance. Now this charges has two options, whether it can go over here or it can go over here. So it has two options. Now what option will it choose? Now the main objective, that is this point, this potential and this potential, is pushing the charges to go from this point to this point. So this charges is trying to get over here with minimum resistance. That is their objective, that is minimum resistance. So that is their objective. So a certain part of Q will travel over here and a certain part of Q will travel over here. Now depending upon this RA and RB, if RA is very much, that is the resistance is too high, then less amount of Q will flow over here. Why? Because it is hindering. So a bit, that is high amount of current will flow over here. So that is what we come to know. So now there is a difference of flow of charges. So this we know. After that it comes back and joins to its original position and the same amount of current I flows over here. So this is what actually happens. Now if you look at the total current that is traveling, the total current I is actually equal to, if you go over here, what is the total current that is traveling over here? That is potential at this 2 point, potential at V1 divided by R1. And potential at this point is V2 divided by R2. Now if you notice, see this is the potential, so this potential is same at this point. Now if you look over here, the potential will be constant. Now see, for both the cases potential will be constant, that is potential to travel is constant. Now the resistance is increasing, therefore the charge is decreasing. So we know that potential at this point and potential at this point is actually equal because they are connected in parallel. So see, this is the same wire. If you look, this wire is being connected into two different parts. So now we know that potential over here, these two potentials are same. Now if you ask me why, the question is why potential is same. This is the question that I often come across. Now the reason why the potential at these 2 points are same, because, so now you have to understand this. Say suppose what was, I can draw this in this fashion also, but not, if you don't want to get confused, this was my diagram. So what you need to understand when you ask me the question why potential is C. Now we define what was potential. Potential was the presence of electron. Potential was the presence of electron. How much electron is present. Now if you look over here, there are two divisions. So electrons will be carried equally in these two wires. But why is there a difference in current then? If electrons are carried equally in these two wires, we know current is nothing but the flow of these electrons or this charge in unit time. We are talking in unit time. So the amount of that is the amount of charge that is flowing over here. It may be electron, I am not specifying, but let's talk this about charge. So the amount of charge that is flowing at this unit of time should be the same that is flowing at this unit time. So in both the cases, we know potential is the presence of charges. Sorry, every time I'm using electrons, let's say it's charges. So potential is the presence of charges. How much charge is present over here and how much charge is not there in this position. That is the potential that you can imagine. This is the potential that you can imagine. But one thing that you have to keep in mind is that if you look over here, now the charges, equal amount of charges will be divided. But what you need to see is that why is the current different? As I've said earlier, current is different because the rate of flow of these charges is different. If this resistance is smaller, so the rate of flow will be higher. Now, what was resistance? Resistance was those particles which hinders the movement of these charges. Say suppose this is my charge Q, it wants to move. But if this resistance are closely packed and there are no free electrons, so it will get hindered, it will suffer multiple collisions and then it will come out. So the flow is less over here than here, but equal amount of charges is being carried in this two points. That is why. Now, please keep in mind, this is one of the examples in which I understand what is actually potential. So, if you look over here, V1 and V2 is equal. So, I is equal to V upon, if I take V common, 1 by R1 plus 1 by R2. So, now, let's write this in our next slide. So, now we have V equals to I upon, let's do this previously so that you don't have any confusion. After that, I'll write another step for your understanding. I was equal to V upon 1 by R1 plus 1 by R2. So this is what we got. So if you write V is actually equal to I, this comes down, or this particular thing goes up. So if you simplify this, this is actually equal to, let this be R equivalent. Let this be R equivalent. So R equivalent is this. Now what is R equivalent? R equivalent, 1 by R equivalent was 1 by R1 plus 1 by R2. Why? Because V was written as V by R equivalent and 1 by R equivalent was 1 by R1 plus 1 by R2. So this is the formula for parallel connections. So now if you look at this particular diagram, this is A, this is B. Now if someone says that I don't know what is happening in this wire and this wire individually, just tell me what is the equivalent resistance, that is what is the overall resistance because of this. If I draw this in a box, say suppose this is A, this is B. I am not concerned at what is happening in here. So what is my equivalent resistance? And that equivalent resistance is given by this formula. 1 by R equivalent is nothing but, since this is R1, R2 divided by R1 plus R2. Therefore, R equivalent is R1 R2 divided by R1 plus R2. So this is your formula for parallel series. Now say suppose someone tells me I have joined another and another charge. That is, another and another resistance. So if you have joined say 1, 2, all you have to do is 1 by R3 plus 1 by R4. So this becomes R1, R2, R3, R4 divided by in the numerator, that is R1 plus R2 plus R3 plus R4. So this is how you calculate your equivalent resistance in parallel.